So just a quick synopsis. An angular momentum, particle mass m, and a circular arc radius r is just I omega. I is mr squared for particle at distance r from the axis. And omega is the angular velocity. R omega is v, so this is also mvr. Elliptical orbit of a satellite around a planet. Apogee the furthest, perigee the closest approach in an elliptical orbit. And orbits are typically elliptical. Angular momentum has to be constant. Now there's a reason for that, which is simply that the planet is always exerting a force toward itself. And the planet is the center of the planet's the axis of rotation, right? So the force is always toward the axis of rotation. How much acceleration you think you'd get out of that system if you pushed from the end of the rod toward the axis of rotation? You'd have no force perpendicular to the beam. It wouldn't accelerate. You just maybe knock the system over, but it wouldn't rotate. Maybe you understand that, maybe you don't. We'll talk about that in more detail, but that's why, very simple reason, in an orbit you have no change in angular momentum. So if you accept that, you get this. You also know that the change of kinetic energy is equal and opposite to the change of potential energy, which is this, and it's just a simple integral. Okay? With these two conditions, you can figure out from the velocity here what the velocity will be here and what the radius will be here. Okay? So you figure out how close the satellite will come to the planet, which is very convenient if you're trying not to crash your spacecraft into Mars. Because if the closest approach is within the radius of the planet, you're going to crash, right? Okay? Just another plug not to be crashing your spacecraft into Mars, right? Watch your units. And here's another application.